recording again. Following Zoom session is being recorded and will appear later today on my YouTube channel, Math with Mayo. There are 2 different classes that may be observing this session. Therefore, when you participate in the Zoom meeting, if you do not wish for your picture or your name to be made public, please leave the video off and use an alias name. If you have questions during the meeting but do not wish to speak, email me at bmayo@ybcc.edu, and I will respond as soon as I can. I will have us take a break later, and if I forget, you remind me, but I didn't think we needed to take a break so soon. So we'll continue on now, and we're going to look at section 11.7. Okay, and in 11.7, we've got 2 new formulas, though one of them is really just a different variation of another formula. But before we do that, let's review the formulas we've had so far this chapter. We've had A equals P times 1 plus R over K to the KT power. Compound interest formula, where it is not compounded continuously, but it's compounded annually or semi-annually or quarterly or monthly, etc. Okay, where K is the number of compoundings. Then we've had the formula A equals P times E to the RT power. This is where you've got something that's being compounded continuously, or you've got a population that's growing or decaying. And that's where you use E instead of the first formula. We also had a formula that said time equals natural log of 2 over R. This was if you had something growing continuously and you wanted to know the doubling time. You could use this formula, but you could also use this shortcut. The natural log of 2 divided by the growth rate equals the time. Okay, now in this, and then we've had the change of base formula. So let's see, log base B of, forget what they use, is it X? Let me look it up here really quickly. Yes, X equals log base A of X over log base A of B. So we've had that formula. Now, 2 new formulas. One of them looks like this, P equals P sub 0 e to the KT. Now, in reality, this formula does the same thing that this formula does. It just has some different letters standing for the same thing. For instance, here, P is the initial amount, A is the ending amount. Here, P sub 0, or P naught as it's called, is the initial amount, P is the ending amount. Here, R is the growth rate. Here, K is the growth rate. Time is still time, E is still E, all right? So they introduced this formula, but really we could use either of these 2 to accomplish the same thing. And then there's another new formula called the radioactive decay formula. We'll come back to those in a minute, all right? Or perhaps more than a minute. First of all, I'm going to look at solving some equations. This says 6 to the x minus 2 power equals 36. Recall in a previous section, we said that if we had a base raised to a power equals the same base raised to a power, if the bases were the same, then the exponents would be equal. Well, what I can do with this problem is I can take 36 and write it as 6 squared. So now the bases are the same. So I can take the exponent on the first expression and set it equal to the exponent on the second expression. Okay, so if I can rewrite the equation so they have the same base, then the exponents are also equal. Well, if x minus 2 equals 2, if we add 2 to both sides of the equation, we get x equals 4. Let's check our work. 6 to the 4 minus 2 power equals 36. 6 to the 2 power equals 36. 36 equals 36, and it checks. Any questions on this example? All right, let's take a look at this one. 8 to the negative 2x plus 1 power equals 1 over 64. All right, well, I can take 1 over 64 and write it as 1 over 8 squared. But I can take 1 over 8 squared and write it as 8 to the negative 2 power in the numerator. So now I have 8 to a power equals 8 to a power. So the exponents are equal. So we form an equation using the exponents once we have the bases the same. So the key to this problem is to manipulate it to where you get to you have the same base on both sides of the equation. All right, so now let's see here. Subtracting 1, we get negative 2x equals negative 3. Divide by negative 2, x equals 3/2. Well, let's see how that checks out. 8 to the negative 2 times 3/2 power plus 1 equals 1 over 64. 8 to the, well, negative 2 times 3/2 would be what? Negative 6/2 or negative 3. Negative 3 plus 1 would be negative 2. That would be 1 over 8 squared, which would be 1 over, oops, 64. So the answer checks. All right. Let's see here. Now, this says 7 to the x power equals 12. Well, we've got a problem here, because if I'm going to use the same method I've been using on the previous examples, I've got to figure out how to take 12 and write it as x to some power. The last two examples, it wasn't too bad to figure out what to do, but here, I don't know how to do that. I don't know how to take 12 and write it as 7 to some power. So we're going to try a different approach. We're going to take this exponential equation and rewrite it as a logarithmic equation. It's going to become log base 7 of 12 equals x. Okay, that's the old playing baseball. The base is the same, but the players change places. Okay, I'm going to rewrite that, and now I'm just going to put x on the left because I want to work on the side that has log base 7 of 12. I can now use the change of base formula and punch that into my calculator. Log of 12, close it up with parentheses, divided by log of 7, close it up with parentheses, 1.276989408. In the directions, let's see, it says round to 4 decimal places. So I'm going to round to the 9, the 8 is going to round up. So I'm going to get 1.27. Oh, that would be 70, wouldn't it? Okay. So in this case, because I couldn't make the bases the same, I changed it to a logarithmic equation, which isolated x, and then I used the change of base formula. Okay, let's see here. Let's do another one of those. Here we have 5 to the x plus 1 power equals 3. I don't know how to take 3 and write it as 5 to some power. So again, I'm going to use the change of the changing it into a logarithmic equation. So log base 5 of 3 equals x plus 1. Oh, but now I've got to subtract 1 from both sides. So I've got log base 5 of 3 minus 1 equals x, or x equals log base 5 of 3 minus 1. Now be careful, that minus 1 is not sucked inside of that log. It's a whole separate term. So using the change of base formula, I'm going to use natural log this time. Natural log of 3 over natural log of 5, and then a whole separate term minus 1. Let's see what we get. Natural log of 3, close it up, divided by the natural log of 5, close it up, and then minus 1. And I get negative 0.31739, going out 4 places. The 9 is going to round up, so we're going to get negative 0.3174. And again, when I use the change of base formula, I can have the top and the bottom both natural log, or the top and the bottom both common log. Any questions about this? All right. This next one says solve each equation, give the exact solution and an approximation to 4 decimal places. Same kind of idea, except now I've got e to the 3.3 t power equals 9.1. Again, I have no idea how to take 9.1 and write it as 3 to some power, or e to some power, or to take e and write it as 9.1 to some power. So those first few of this section, I did that way because it was quick and easy, or at least for me, it was easier to get the same base. But when you can't, then you end up changing it to a log. So this becomes log base e of 9.1 equals 3.3 t. But isn't log base e just natural log? So this is the natural log of 9.1 equals 3.3 t. Divide both sides by 3.3, and we get t equals the natural log of 9.1 over 3.3. We didn't need to use the change of base in this case because the base was base e, which then becomes natural log. Anyway, let's see what we've got here. Natural log of 9.1, close it up with parentheses, divided by 3.3, 0.669174065, rounding to 4 places. The 7's going to round up, so 0.6692 is our solution there. All righty. Let's see. How about this problem? It says solve each equation. All right. I've got log of 5x equals 4. Keep in mind, this is common log or log base 10. Even though there's no base written, there is an implied 10 there. Also remember back towards the beginning of this chapter, I said, when you're solving a logarithmic equation, there's a good chance you'll change it into an exponential equation to solve it. When you're solving an exponential equation, there's a good chance you'll change it into a logarithmic equation to solve it. We're going to take this logarithmic equation and write it as an exponential equation. It's going to be 10 to the 4th power equals 5x. Okay. Then we're going to divide both sides by 5. So we get x equals, let's see, 10 to the 4th power would be that. Divided by 5 would be what? 2,000? Okay. Any question on that? You could check your work quite easily. You could say, well, let's see, log base 10 of 5 times 2,000. Does that equal 4? LOG of 10,000. See what you get. Okay, let's see. LOG 10,000. Yep, it checks. All righty. How about this one? The log of the quantity 2 minus x equals 3. Solve this equation. Again, don't forget there's an implied base 10 with the log. So then 10 cubed equals 2 minus x. 1,000 equals 2 minus x, 10 to the 3rd, 10 times 10 times 10. Okay. Subtract 2, we get 998 equals negative x. Divide both sides by -1 and x equals negative 998. Okay, let's see here. All right, how about this one? We've got the natural log of 3x plus 1 equals the natural log of the quantity x plus 7. Well, since we're taking the natural log of both sides of the equation, the quantities inside parentheses can be set equal to each other because on both sides we've got the natural log. And there's a way to go through all that, but that's beyond the scope of this class, so we'll just stick with it at this point. All right, I'm going to subtract x from both sides. 2x plus 1 equals 7. Subtract 1 from both sides. 2x equals 6. Divide by 2 to both sides. X equals 3. Let's check our work. The natural log of 3 times 3 plus 1 equals the natural log of plus 7, excuse me. The natural log of 10 equals the natural log of 10. And yes, it does. So x equals 3 is correct. Okay, let's see here. How about, let's do this one. 5 to the x plus 4 power equals 125. Well, in this case, I can go back to what I did at the beginning of this section because I can take 125 and write it as 5 cubed. So now that the base is the same on both sides of the equation, we can set the exponents equal to each other. Subtract 4, x equals -1. Right then. Now, I said we were going to look at some new formulas, and we're going to start that now. So the formula we're going to look at now says radioactive decay formula. And it looks like this. A equals A sub 0 times 2 to the -t over h power. Let's see if I can write that bigger. -t over h power. All right. This is basically a half-life formula, all right? And how exactly does a half-life formula work? What is that whole idea of half-life? Well, let's say we have a population of Snickers bars. I know they're not alive, but I just like using Snickers bars. And I put 64 Snickers bars in the refrigerator. And I come back 1 week later, and only half of them remain. There's 32 Snickers bars in there. The rest of them had disappeared. Okay. And then I come back 1 week later, and there's 16 of them. Half of the 32 have disappeared. And I come back 1 week later, and there's 8 of them. And then there's 4, and then there's 2, and then there's 1, and then there's a half, and then there's a fourth. Okay. For this example, we would say that the Snickers bars have a half-life of 1 week. That means that at a given time, 1 week later, half that starting population will disappear. Now, 2 half-lives do not a whole life make. In other words, because we lost 32 the first week, doesn't mean we lose 32 the second week. Each week, we lose half of what was there at the beginning of that week. Okay? Now, half-life, you might expect something like this, because if you'll recall from way back when we were graphing this, the graph of this thing looked like this. It was decreasing. As x increased, y got cut in half. So how do we get this to look like this? Well, all right, consider this. Isn't that the same thing as that? In other words, if we have 2 to the -x, wouldn't that be 1 over 2 to the x? And 1 to the x power is still going to be 1. So we could go from there to here. Okay. So basically what I'm saying is this is equal to that. Now, what does it have to do with anything? So let's go back to this formula. Here, they could have written this formula like this, with a positive t but a base of 1/2. For whatever reason they didn't, they used a 2 to a -t power over h, -t over h power. But I just want to assure you that this is a half-life formula. The population gets cut in half every time the half-life period happens. Okay, so back to this. A equals a sub 0 times 2 to the negative t over h power, where a sub 0 is the beginning amount and a is the ending amount. All right. Okay, here we have a problem. It says tritium, and I don't know if it's tritium or tritium, but it says tritium decay. The half-life of tritium is 12.4 years. So that means that every 12.4 years, half of what's there at the beginning disappears. How long will it take 25% of a sample of tritium to decompose? Okay, so we know the half-life. The time is the question, how long? We don't know that. We've got the beginning amount and the ending amount. They don't tell us what the beginning or the ending amount is, but they do say this: how long will it take for 25% of the original amount to decompose? So let's call the original amount a sub 0. Let's just call it a sub 0. All right. But the ending amount, a, is the result of losing 25%. 25% decomposes. So that means we have 75% of the starting amount left, which means a equals 0.75 a sub 0. Now, it said 25% decomposed, so 75% is still left, and 0.75 is the decimal equivalent. Okay. So now I'm going to replace a with 0.75 a sub 0. A sub 0 remains a sub 0 times 2 to the negative t divided by 12.4 years power. Recall at the end of Thursday's session, we had some problems where we didn't know the initial amount, but we talked about doubling it, and we ended up dividing both sides by the unknown amount. Same thing here. We can divide both sides by a sub 0, and we don't need to know what a sub 0 is. So we get 0.75 equals 2 times negative t to the 12.4 years power. Okay. So now I have an exponential equation with nothing in front of the base over here. Okay. So I'm going to change this into a logarithmic equation. It's going to become log base 2 of 0.75 equals negative t over 12.4. All right. I'm trying to solve for t. If I come in and multiply both sides by 12.4, that would get rid of that 12.4. But what I'm going to do is I'm going to multiply actually by negative 12.4 so that all in one step I get rid of the 12.4 and the negative. So now what I have is t equals negative 12.4 times log base 2 of 0.75. And I just switched the whole thing around because I wanted to have t on the left side. Any questions so far? So my next step is going to be to use the change of base formula. So I'm going to have log of 0.75 over the log of 2. So going to the calculator, negative 12.4 times the log of 0.75, close it up, divided by the log of 2. Make sure that you're using the same log in both cases. I'm getting 5.146464991. And let's see, they rounded to the nearest tenth of a year. So the 4 would round down. So time equals approximately 5.1 years. Any questions about this particular example? All right, let's do another example. Thorium decay. An isotope of thorium, written as 227Th, has a half-life of 18.4 days. How long will it take for 80% of the sample to decompose? All right, so again, we're using this half-life formula. Okay, and we're told that the half-life is 18.4 days. Time is the unknown. It says, how long will it take for 80% of the sample to decompose? So we don't know our beginning amount or our ending amount. So the beginning amount we'll just leave as a sub 0. The ending amount is the result of 80% decomposing. It says, how long will it take for 80% to decompose? So the ending amount is equal to 20% of the beginning amount, or 0.2 or 0.20, either way. Okay, so A equals that. So now I get the following equation. 0.2 A sub 0 equals A sub 0 times 2 to the negative T over 18.4 days power. And if there's any questions, please stop me and let me know. Next step, we're going to divide both sides by A sub 0. So we get 0.2 equals 2 to the negative T over 18.4, and that's days. I'm going to change this into a logarithmic equation. Log base 2 of 0.2 equals negative T over 18.4. You can see this problem is pretty much like the last problem, except we're dealing with 80% going away instead of 25% going away. Okay, we're going to multiply both sides by negative 18.4. So we get rid of the 18.4 and the negative all at once. So T equals negative 18.4 log base 2 of 0.2 using the change of base formula. Log of 0.2 divided by log of 2. And let's see here. So negative 18.4 times the log of 0.2, close that up, divided by the log of 2, close that up, 42.72347, etc. And let's see here, they round to the nearest 10th, and this is days. Time was in days, right? Okay, 42.7 days. We're going to take a break, so I'm going to pause the recording. All right. We have a new problem. This says carbon-14 dating. A bone fragment analyzed by archaeologists contains 60% of the carbon-14 that is assumed to have been to have had initially. How old is it? Sorry about that. Okay, so again, we're using the formula A equals A sub 0 2 to the negative T over H. A bone fragment analyzed by archaeologists contains 60% of the carbon-14 that is assumed to have had initially. How old is it? So time is the unknown. Now, it doesn't tell us in this problem, but in a previous problem, it told us the half-life was 5,700 years. And no, I don't expect you to remember the half-life of carbon-14, okay? But here's where things are a little bit different. It says a bone fragment contains 60% of the carbon-14, okay? So they don't tell us how much is initially there, but they tell us how much is there at the end. So this is 60% of that, or 0.6 of that. Now, the previous problems, one of them said 25% decomposes. Another one said 80% decomposes. So those told you how much was going away. So we subtracted those from 100%. This one is telling you how much is still there. So it's the same as if it had said 40% decomposes. All right. So you've got to read the problem carefully. Is it telling you what leaves or what's still left? All right. So now we get 0.6 a sub 0 equals a sub 0 times 2 to the negative t over 5,700 years power. We'll divide both sides by a sub 0, and we get 0.6 equals 2 to the negative t over 5,700 years power. We can now change this to a logarithmic equation and get log base 2 of 0.6 equals negative t over 5,700 years power. We can then multiply both sides by negative 5,700. And the 5,700s go away, the double negatives go away, and we get time equals negative 5,700 log base 2 of 0.6, which is negative 5,700 log of 0.6 over log of 2. And let's see what we get there. So negative 5,700 log of 0.6, close it up, divided by log of 2, close it up. And I get 4200.073887. And they say about 4,200 years. Which reminds me, there's problems in the homework and perhaps in the test that are like this, and people often miss it because they don't read the directions carefully, okay? I believe in those cases, it'll say something like round to the nearest 100 or round to the nearest 1,000. Be sure to read all of the directions. Don't just assume, oh, it's going to be just like the last one. Read the directions carefully. Okay. All right, now, this says compound interest. If $500 is deposited in an account paying 8.5% annual interest, compounded semi-annually, how long will it take for the account to increase to $800? All right, the key to this problem is that it compounds semi-annually, not continuously. So we're going back to using this formula, okay? All right, so let's see here. $500 is deposited, so that's P. 8.5% annual interest, so that's R, which is 0.085. Compounded semi-annually, so K is 2, and T is the unknown. And we want the final amount to be $800. So we're going to make $300 in interest. How long is it going to take? So our equation becomes $800 equals $500 times 1 plus 0.085 over 2 raised to the 2t power. Okay. Now, I can go through and take 0.085 divided by 2 and get the result and add it to 1 and simplify what's inside of there. Okay. In fact, let's do that. So let's see, we get $800. $500, 1 plus, if I take 0.085 divided by 2, I get 0.0425, and that's raised to the 2t power. Then I can take 1 plus 0.0425 and get 1.0425 raised to the 2t power. Now, I need to be careful. I can't change this exponential equation into a logarithmic equation yet. I have to get rid of that sort of coefficient out there in the front, okay? So to get rid of that, I'm going to divide both sides by $500, okay? On the left side, the dollar signs go, the double zero goes. I've got 8/5, which is 1 3/5, or 1.6, okay? 8/5, 1.6 equals 1.0425 raised to the 2t power. Okay. Now I can change this to a logarithmic equation. Log base 1.0425 of 1.6 equals 2t. All right. Now, I could divide both sides by 2. And instead of doing that, I want to do this just because it'll look a little bit cleaner. I'm going to multiply both sides by 1/2. Isn't dividing by 2 the same as multiplying by 1/2? So on the right-hand side, I've got t, which I'm going to move over here. And then I've got 1/2, but I'm going to use the change of base. Log of 1.6 divided by the log of 1.0425. And I did all of that just because I wanted to have that 1/2 out in front. In fact, well, let's see, how could we do this? We could say parentheses 1 divided by 2. 1 divided by 2. Oh, that's just 0.5, isn't it? So why don't we just do this? 0.5 log of 1.6 over the log of 1.0425. I'm just kind of simplifying things to make it easier to put into the calculator. Divided by the log of 1.0425. And let's see what we get here. We get time is about 5.6 years, and that again is rounding to the nearest tenth of a year. Okay. Let's see here. Let's do one more of those. Compound interest. If $1,300 is deposited in a savings account paying 9% compounded quarterly, how long will it take the account to increase to $2,100? So compounded quarterly, again, we're using this compound interest formula. Okay. Let's see, it says $1,300 is deposited in a savings account paying 9%. Compounded quarterly, so 4 times a year. How long will it take to increase to $2,100? So we've got everything but time. Okay, so what do we got? What do we have here? We've got $2,100 equals $1,300 times 1 plus 0.09 over 4 raised to the 4t power. Okay. So that's $2,100 equals $1,300 times 1 plus, if I take 0.09 divided by 4, I get 0.0225 to the 4t power. $2,100 equals $1,300 times 1.0225 to the 4t power. Okay. But again, I've got to divide both sides by $1,300. So on the right side, we get 1.0225 raised to the 4t power. On the left side, the dollar signs go, a couple of zeros go. Oh, I've got too many zeros on that one. Sorry about that. hang on. That should have been $1,300. Okay, so those go, and that goes 21 divided by 13. I'm just going to leave that as 21 divided by 13 because it doesn't come out nice. Let's see, what does it come out to? 1.615386 anyway, for whatever. Okay, so now I've got log base 1.0225 of 21/13 equals 4t. I'm going to multiply both sides by 1/4, which is the same thing as what? 0.25. So I've got t equals 0.25, change of base, log of 21/13 divided by log of 1.0225. And I know I put several steps in there. I did the same thing I did in the previous problem. Instead of dividing by 2, I multiplied by 1/2 and changed it to 0.5. Here, instead of dividing by 4, I multiplied by 1/4 and changed it to 0.25. Otherwise, you get a 4 down in the denominator of your fraction, and it's just harder to deal with. If anybody has any questions about that, I'm happy to go through that other method though. So let's see, we've got 0.25, and then the log of parentheses 21 divided by 13, close parentheses, 13, close parentheses, divided by the log of 1.0225. And I get t is 5.3883. So we're going to say t is approximately 5.4 years. Okay. So there we have it. Any questions? So a reminder, so tonight you're going to do 11.6, which there's only a few problems there. Also 11.7, and then the chapter review. Tomorrow during class, we'll review for your chapter 11 test, which will be due by 11:59 p.m. tomorrow night. And then starting on Wednesday, we'll go back. Wednesday, we'll review the first 2 tests you took, Thursday, the second 2 tests, and then next Monday, the last 2 tests that you took. And then that following Tuesday will be your final exam. All right, well, if you don't have any questions, I'm going to stop the recording